Hello. Um, we are going to be doing the final step of the presentation process. Where we're going over the SBM trailers, Coletrain. This is the final presentation for ME498, and the following team members are Taylor B, Ethan Myers, myself, John Scotto, and Cole Tinsley. The contents that we'll be going over in this presentation are going to be the following: introduction, design methodology and design calculations, design analysis, design results and specifications, physical prototype considerations for the second step in senior design, conclusion, and the references. The team member roles. Team leader is Taylor B, where he oversees the project, manages timelines, and ensures milestones are met. Coordinates team meetings and external communications. The design engineer would be Ethan Myers, where he develops CAD models and conducts FEA to validate structural integrity of the machine. He resolves design challenges and ensures compliance with legal standards. The investment relations is myself, John Scotto, where I'm in charge of the source funding and I secure partnerships and I build relationships within the community. And the lead researcher is Cole Tinsley, where he collects data to improve functionality and identify areas for optimization, researches future and current technology trends for implementation. Background of project and design goals. The project aims to develop a hay trailer that is road legal and compatible with a 53-foot NHTSA approved semi truck trailer. Primary objectives include creating a self-loading and unloading trailer to eliminate the need for seasonal labor, improve operational efficiency, and reduce workplace risks associated with manual hay handling. Initial focus on small square bales, 14 by 35 by 18, weighing up to 60 pounds, with adaptability for rapid collection and unloading at ports. Design goals: prioritize simplicity, safety, durability, and ease of maintenance. Weeks 1 through 4, finalize design concepts and materials. Week 5 through 8, develop CAD models of components. Week 9 through 12, conduct finite element analysis and address structural concerns. Week 13 through 16, refine and finalize design. Week 17, prepare funding and material acquisition. The milestones: completion of CAD designs, early November, successful FEA simulations, end of November, brochures, middle of November, first round of funding, end of November / early December. Project timeline and milestones. This is the final timeline just for this term, for this semester. We'll be going over an additional timeline in the near future for the second half of our project. Preliminary costs. Estimated total cost, roughly $2,000. Individual component costs. Steel components, roughly $1,400. Rollers, $280. Chains, $170. Wheels, $32. Cost saving measures taken: using existing components such as the motor and the trailer, substituting materials like wood for steel when feasible.
I'm Cole Tinsley, and I'll be going over some of the design processes that we went through, as well as some of the constraints that we were working under. The initial process started with preliminary design sketches. These are some 2D designs that each of our team members set forward. The one on the right side was not the full computer program 2D sketch that Ethan set. It's just the one that I could get my hands on under some issues that we had in communication. The the image that I set on the left side is a piston design that I thought would help with stacking the bales. Taylor's method with the flipper also would help with stacking, whereas I wanted to lift the elevator so that the bales would stack naturally on top of each other. Taylor wanted to set them horizontally next to each other and then flip them upward. Scotto's method, I think, had to do with two different elevators that would run and move up and down so that they would stack and then they would be pushed backward. Ethan's he had several on this particular page, and some of them were more elaborate than others. The one on the very top of it had, I think, 3 different elevators that would work in tandem to sort the bales. Those were just the preliminary sketches. I think we've talked about those in previous presentations. Right. Some of the problems that we ran into with our design process were in terms of weight, cost, and complexity. Those all kind of fall under the scope, this, the scope, the umbrella of scope. The solutions ended up being reducing the scale of our project that we're doing this year and having a separate design to the side that would be at a fuller scale for commercial use, with our current project being more of a proof of concept. A funding brochure was made, I think, by Scotto and with some help of Taylor, and we've been trying to get that out to suppliers and people that could help us actualize our project. Uh, the final design came together because of a collaborative process. We all sat down at a table and said we were going to finalize something, and we got it together. That ended up being our final design. One of the considerations that we had to take for this project were the calculations regarding our safety factor and a lot of the connection pieces. For some of the difficulty with this project is that with a full-size trailer, it would have been many more calculations in terms of stresses in the members and making sure that everything is within code. For a reduced design that we're doing for this project, it was a little simpler. We decided to focus on some key points that were absolutely crucial for our safety factor design. We decided to calculate the forces acting on the highest shear spots. So we analyzed the shape of our design first, and then we analyzed what what the maximum stresses there were. We used a computer program. We used Python to plot the shear bending moments there, so that we knew exactly what our materials needed to stand up to. Chain deflection was another issue that we kind of thought about, especially since we want this trailer to be road legal so that we can use it on plot and on farm plot and on highway. That's kind of another one of the big draws of our design, was that it reduced that transition process from farm to road. The rollers are what's kind of bearing the load of the bale, so we needed to calculate the amount of torque that they needed to put out so that they could bring the bales up into the back of them without any issue, and we ended up having no problems in that area because our motors that we're using for those rollers are sufficient. The codes and standards that we considered for this design, things that are pretty important, especially since we wanted this to be a road legal design that we could move from place to place, and that proof of concept would function. ABE standards, load limits, braking systems, road transport safety, basically all of the things that you need to take into account for getting farm equipment from one place to another via highways and stuff like that, public roads. MVSS compliance has to do with things that are on a farm, side lamps, reflective devices, tires that are made for that environment, impact guards, because the farm is not, obviously it's not as even and functional as a normal road.
So, this design started out as a project to make it possible for a farmer to take his semi-truck or have one of his operators take a semi-truck off of the highway that goes straight to the port or wherever the hay is going, right onto a field, and start picking up square hay bales. the square hay bales in their densest configuration with the most moisture and the densest hay mix could get up to 60 pounds. So to address this, we created a flatbed semi-truck trailer. We would assume that we would purchase a used one, and therefore the only thing consistently that we thought of, there would just be a flatbed, and we would get a unarched. So some flatbeds have an arch in the center to accommodate weight. We would get an unarched flatbed, and then we would have some custom fabrication work, make all the mounts. And then on top of this flatbed, we would have a telescoping, counterweighted hydraulic arm to pick up the bales off the ground, and then they would load them individually into stacks on a sort of dump bed, and then once the stack was full, the dump bed would raise up and the stack of bales would fall to the back, therefore allowing for an entire 53-foot semi-truck trailer to be filled with hay bales picked up off the ground without the farmer or the operator having to get out of his cab. So, on top of the conception that we need to have something that can be adapted to a bunch of used trailers, therefore it will require a little bit of fabrication. The other thing that was passed on to the next iterations of this design was the fact that there needed to be some sort of system so that the operator or farmer could see the incoming hay bales and line the semi-truck trailer up with correctly. And also there needed to be some way that the farmer could ensure that there were no jams on the equipment while it was running, so there wouldn't be some catastrophe and you just couldn't hear it over the radio or something. So to address this, the whole trailer is covered in cameras. There's only 2 or 3 spots that needed to be covered, but it'll be handy for the farmer. We assumed that it would be annoying to have to look down on the screen the whole time, so we also created this sort of laser pathfinder that would outline the vector that the hay bales need to be going in so that the arm can pick it up. So if you imagine the truck driver's just driving along, he sees a red laser light going out in front of him. And if the red laser just isn't bright enough due to it being a super sunny day, or maybe the hay bales have had some more hay grow underneath them and there's kind of an obscurement because of little hay stalks underneath it, you can also rely upon the camera. Okay, so this is our current 3D CAD model, and with it we have made some 2D production drawings that are not pictured. Our current trailer model, as described, is the small scale, small budget one. So we have the boat trailer, and we have this contraption that hangs over the side of it. And just a thing to point out while you guys are looking at this, we are missing in the model the shaft fasteners. So it's hard to see without zooming in, but on the motor, and especially on the wheels, the way that they have a round shaft going through them. So there's no real way for the round shaft to transfer torque without this thing called a key. So they're actually what are called D shafts, and they have a little key that goes in there. But modeling those was computerly cumbersome when rendering things, so we kind of omitted them. And then there's also these things called shaft collars that prevent the shaft from going laterally. A shaft collar looks like a bunch of washers together with a bolt sticking out the side, and it just prevents the shaft from moving in and out of the holes it passes through. So, how does the trailer work? Well, there is a singular hay elevator motor, and it runs a belt down. So at the RPM it's running at, it slows down a little bit and touches the ground. Touches these rollers that are just above the ground, and on that same shaft are some rollers that do touch the ground, but those rollers are free floating. So the free floating rollers go along the ground as the trailer drives along, and then the little rollers are spinning with a torque applied, and then when those make contact with an incoming hay bale, it lifts it up onto the hay elevator, up and over onto the hay trailer, and then when there's too many, it'll just push it out the back, or maybe catch on the cross members. So this pictured is the non-highway legal configuration of it. It's designed so that you can go back and forth between a highway legal and a highway non-legal one. So this extended version will pick the hay bales up, put them on there. The unextended version, you can actually take that extended out arm thing and push it up where the two close together hay bales are, and it just all compacts together. And also, while it's in the non-highway legal configuration, it uses that second. Well, in this picture, it's not the second. It uses the only trailer hitch on there. That trailer hitch is designed to be moved back and forth to save money, but the hay, not sure if you can see my mouse, but if you see where it is now, it'll hop over to where the bigger center piece of extrusion is, so that I can drive down the road without it sticking out 5 feet offset from the center line of whatever vehicle's towing it down the highway. Okay, so cost analysis. We already have the boat trailer, we already have a motor, and we actually have a few motor options from around the school. As it comes out, the big expensive bit is all the steel tubing. We use an 1/8 inch thick walled steel tubes of various sizes, and we are limited by what is available, especially with the odd sizes, and how thick we can get it. And that is just from McMaster-Carr. We have not done research yet into local steel suppliers because it will fluctuate a lot, and McMaster-Carr prices seem to have been going up significantly over the last few years, especially with steel. Okay, so FEA and CFD. So those standing for finite element analysis and computational fluid dynamics. This was all done using Fusion 360. So Autodesk's built-in FEA and CFD tools. And this experiment, we did not need to use CFD because the trailer will be moving at such low speeds when it's all extended out. On the highway, yes, it will encounter higher speeds, but this is just a prototype. It's not meant to go on the highway. So we didn't feel like it needed to be tested. It will just be secured if it ever needs to go above, very low speeds. But it's not what it's being tested for. So the test we did run, we ran some just stress tests. We knew what the maximum weight of the trailer was, and we knew what it's rated for based off of its hitch size, and we knew that includes the maximum tongue weight, so how much you could be standing down directly on the trailer mount and how much it's pulling at it. And so that created a nice little vector for us to test on the offset, and it will be nowhere near either of those values, but this is just somebody put our thingy on there and then also put their oversized boat on there. What would it do to the offset going down the highway? Even though it won't be going down the highway, this is just the maximum possible amount of stress it could endure, and it didn't do great. Surprisingly, we didn't think that front bar would be the failure. We thought just the cross member. The cross member is not doing too great. We did know that the bolt holes were going to have issues.
There's definitely a lot more specifications that we can include here. However, because this is such a complex system and because we have so many that we can include, we just had to cherry pick some important ones. In our final report in the appendix section, we have a lot more tables and a lot more sections going over the motors and the drive system and some of those key specifications for those. Here are a few of the considerations as we enter the second portion of this project. We're going to go over the planning, the costs, the time considerations, and delivery results. First, we really want to simplify the design and focus on some of our key functions, such as the hay conveyor and the actual offset system of the hitch. Additionally, we want to utilize lightweight materials when able, such as wood in place of steel, because as the design started to go, it was clear that the weight was starting to grow pretty fast. We plan on fabricating the hay elevator and the roller system all from scratch. using some of the materials that we get from our local sponsors or funding that we acquire from the first portion of this project. We plan on fabricating the rollers and the frame from scratch because otherwise we'd have to buy them. It'd be a lot more expensive, and in order for us to keep our costs down, we're gonna have to fabricate it. We're gonna focus on a modular construction approach and collaborate with various team members in order to see this through. The cost for this project, as we saw earlier, was roughly around $2,000. Primarily, most of that comes from the metal and the stock material. As we can see, about 70% of that comes from that. 15% comes from the rollers, and then around another 15% comes from various other components, such as the motor, which we bought used, the chain and sprockets. Because of this and because of how expensive and kind of the lopsidedness of the material cost, it's really important to leverage existing connections within the community and to really lean on this funding that we can get. In addition, it's important for us to consider low cost materials such as wood or recycled materials like recycled steel or aluminum. For the timeline for this second port, for the timeline for the second portion of this project, we have a fairly laid out. We have a fairly well laid out plan for how this next term will be going for our project. The first 2 weeks, we're going to be finalizing our funding and acquiring materials to build. From weeks three for the next 3 weeks, we're going to be building the frame, making sure that it's structurally sound and we have a good foundation to base our design off of. From weeks 7 through 9, we're going to fabricate and install the roller and the hay pickup system. From weeks 10 to 11, we're going to conduct the initial prototype demonstration, make sure it works, and kind of go back to the drawing board. For the next 3 weeks, from weeks 12 to 15, we're going to be preparing the prototype for demonstration. Again, really honing it in and refining it. And then lastly, week 16 is when we'll be presenting this. In regards to the delivery and results, we plan on hoping this prototype will showcase our primary functionalities, as stated earlier, the hay pickup system and the movements via the roller system. We want to focus on demonstrating scalable technology for a full-size model, which we can later hopefully move on to. We plan to highlight the simplified yet effective design features and address some of the revelations that we got throughout the design and prototyping process.
For the conclusion, the final hay trailer design incorporates self-loading capabilities, reducing labor requirements and improving operational efficiency. The design minimizes workplace risks by eliminating manual hay handling and incorporating safety-focused features, such as manual locking mechanisms and structural components. Utilizing readily available materials and cost-saving measures, the project achieved an estimated budget of $2,000, with options for further cost reductions. The small-scale prototype provides a platform for testing key features and can be scaled up for full-size operations once proven effective. Decisions like using steel for durability, electric motors for scalability, and collapsible components for transability ensure the trailer is functional, maintainable, and adaptable to various farming needs. I just want to say thank you to everyone for taking the time out to watch our video. We really appreciate it, and I hope everyone has a wonderful and great day.